So section 9.7 is all about inverse trig functions, okay? Section 9.7 is all inverse trig functions, and what I want you to think about with inverse trig functions is you've actually already dealt with these at a very, very basic level in geometry. So inverse trig functions can be denoted as in two different ways. They can either be called sine inverse of something, like this, or they can be referred to as arcsine. And your book actually uses arcsine to refer to them, but know that they are actually interchangeable. So whether you see the words arcsine or whether you see the words inverse sine, or the symbology for that, I guess, either way, those mean the exact same thing. And when you think about that, the way that we actually solve this, remember that if you take the sine of some angle, that is going to be equal to the opposite over the hypotenuse. And if I take the inverse of that, the inverse just switches those two things around, right? So the opposite over the hypotenuse, the inverse of that is equal to x. These two things are just flipped. Arcsine does the exact same thing. So if I say that sine of x is equal to the opposite over hypotenuse, then arcsine of the opposite over hypotenuse is equal to x. These two things are the exact same. I'm just showing you that that's the way that the notation could exist, but you likely will see arcsine a lot. In my notes, I'm just going to use the inverse sign, this symbol, because it's a lot easier and it's a lot quicker for me to write versus writing arcsine. I don't know why your book uses arcsine instead, but they do. Okay, so inverse trig functions can either be written as sine inverse or arcsine. Obviously, it can be done with cosine, tangent, and then all three of the other ones as well. So just so we're on the same page, I'm going to be using this one. Your book will use this one. They are interchangeable. Okay, so what you would have seen in geometry is you would have seen something along the lines of this, where you have a right triangle. You would have an x value right here. This would be like 2, and this would be 5, and then you would be asked to find the angle. And right now, all we have is an x value. But we know right now that the sine of x is going to be equal to 2/5, right? So if I ask you to find the sine of this angle, or if I ask you to find what the angle is, you would have flipped these two things around and you would have done the inverse sine of 2/5 is equal to x. And then that will give you your answer. Now remember, your calculator and your brain have to be thinking in the exact same mode. So if I'm looking for a degree here, your calculator has to be in degree. So with your calculator in degree, you would type in sine inverse of 2/5, and then you would end up with x equals something like 23.5. So you would end up finding out that the value of that would be 23.5 degrees, something close, okay? Now that is a very, very straightforward response. That's a very straightforward thing. But what you have to remember is we eventually learned about law of sines and law of cosines. Now, law of sines and law of cosines was something that actually a lot of you probably preferred to use law of sines a lot because you were really, really good at it. And remember, it was just like the sine of something over the side length. I guess it would be sine A over A equals sine of B over B. This is something that you guys would have used a lot, because if you're given an angle and a side, it's just a proportion, and we're going to set up the proportion and solve the triangle, right? So now we have an angle. So let's call this one like 28 degrees. And then we've got our side lengths, which we have like 27, and we have 43, and we have 55. So we've got angles and we've got sides. The only thing is, and your directions might be something like solve this triangle or solve for x. But in this case, I can't solve for this angle because I have two unknown angles, and I only know one, and I know a triangle adds up to 180, but I can't do anything with it. So what I would do is I would create the law of sines, or I would use the law of sines. So I would take sine of 28 over my one side length. Remember, you go with opposites. So sine of 28 over 27 is going to be equal to sine of x over 55. So now we would go through our whole process and we would be able to solve this entire thing very, very quickly and very, very easily. We would cross multiply, so I'd get 55 times the sine of 28. Again, calculator has to be in degrees here, equals 27 times the sine of x. We would divide each side by 27, So I end up getting something like 0.9563. I worked this out beforehand, so hopefully all my numbers work. 0.9563 equals the sine of x. Now in this case, we would solve for the sine of x by using we would solve for x by using the inverse. So I would take sine inverse of 0.9563, and I would be left with x equals 73 degrees. All right. Now, most of us would be able to take this answer, move on, and be done, right? We would just look at this answer and we'd say, okay, that's great. We got 73 degrees. That's fine. But what you have to think is, remember, triangles add up to 180. So if you remember, Mr. Keller probably taught you to be really, really careful. He probably taught you to be really, really careful with these, because you have to pay attention to your angles. Your calculator is only programmed to give you one angle, and sometimes the angle is right and sometimes it's not. And specifically, I believe you were told to be really careful with the law of sines when you were told that the angle was obtuse. Now again, with geometry, we can't trust a picture. We have to make sure we're paying attention to what the actual work tells us. But if I tell you that this angle right here is 73 degrees, that would mean that I can go through and I can solve for this angle, right? So I'd be able to solve for that angle. So 73 plus 28 is 101, and then that would tell me that this angle is 79 degrees. Why is it not okay for this angle to be 79 degrees and for this angle to be 73 degrees? Anybody?
The longest side is across from that, so the biggest angle would have to be on that side.
Exactly. So this is telling us that this angle has to be the biggest because 55 is the biggest side. So this work, this thing that we've created, can't be correct. So I can't say that the sine of this angle is 73 degrees. So what I need to do is I need to pay attention to what is actually the correct angle. And if I think back to the unit circle, there's two places where the sine of something is equal, right? There's two places where the sine of something is equal. One of the sines right here is 73 degrees. And then I know that the other of those is going to be on this side, because these two values of sine, the y value here and the y value here, are going to be equal to each other. So basically what the calculator just did was it gave us the reference angle. So it told us that the reference angle is 73 degrees. We just have to figure out what that is. So this angle right here is actually 107 degrees. So the angle for x has actually got to be 107. And this is where we're going to really start talking about very, very important ideas in trig and calc. Because we need to start being able to make these connections. We need to start being able to say, okay, this angle is not the biggest angle. Or I'm sorry, this angle is not the biggest angle, so it can't show up to be the biggest angle with my work. What did my calculator give me? Well, my calculator gave me my reference angle, and in this case, the reference angle is right here. I have to be smart enough to know that this is an obtuse angle. So if you go into your calculator and you type in the sine of 73, and you type in the sine of 107, those will both give you the same exact answer, which will be 0.9563. So I know that I found the correct angle, all right? So that's something that you have to think about, and that's something that you have to make sure you understand, because if you don't understand that, that is gonna be kind of tricky, all right? So using that idea and using that thought process, we can then talk about the graphs of sine and the graphs of cosine. So if I think of the graph of sine is a function that looks like this, and it just keeps repeating over and over, and it will actually keep repeating on this side as well, right? So if we think of the graph of y equals sine of x, this is what we end up with. Now I'm going to spare you writing all of the actual, excuse me, what am I trying to say? Units. So we're just going to think, okay, what if I'm going to graph the inverse function of this? If I want to graph the inverse function of this, that obviously means that it is going to be the inverse of a horizontal is vertical. So that means that this thing is going to be flipped, and it's now going to be graphed like this. But as we look at this, this is not a function, right? Because remember, one of the crucial tests for a function is the vertical line test, and I can very clearly see that this thing does not pass the vertical line test. So in order for us to actually deal with this as a function, we're going to have to restrict a ton of this graph. And most of the things that we're going to have to restrict on this graph are going to be the parts that start repeating. So the way that we're going to restrict this is I'm actually going to draw the same curve that I drew the first time, like this, which is what you see here. That's that part of the graph. And then I'm going to restrict it. I'm not even going to let this thing turn this way. Because if as soon as I let it turn back, or as soon as I let this turn back, I've instantly ruined my vertical line test. So what I'm going to do is I'm going to get rid of any part of this that would start to curve back, because I want that to be a perfect one-to-one function. So if I want that to be a perfect one-to-one function, there are two values on here that are important. Okay, one of those values are the x values are important, -1 to +1. And then the y values for this are going to be pi over 2 and -pi over 2. Or I guess if you want to think of this in terms of degrees, because we should be able to think about degrees and radians interchangeably, we have 90 degrees, or you could say -90 degrees, or you could use 270 degrees, either way. But -90 degrees, +90 degrees, 270, whatever you want to think of, like this. But notice that only things in the graph exist in quadrant 1 and quadrant 3. So the only thing about sine is that it exists in quadrant 1 and it exists in quadrant 3. So the inverse of sine will only exist in 2 quadrants, and the only 2 quadrants that it exists in are 1 and 3. Okay? So that's something to kind of pay attention to when you're looking at your graph. So as you deal with those, just make sure that you're paying attention. Just make sure that you're watching. Just make sure that you're seeing what's going on with those things. Okay? Any questions on what you're looking at?
Will it always exist in 1 and 3, or like can you reflect it or something and it would be in 2 and 4?
You could do a lot of things with inverse sine. Like you could change the graph, but just most of the time here we're going to be talking about basic functions. We're going to be talking about basic graphs, which means that we're just going to be using inverse sine and regular sine. Okay, let me pause something for 1 second. For cosine, everything does the exact same type of idea. We can use the same exact kind of idea for cosine. Remember, with cosine, our graph will start at 1 and then it will actually drop down and then come back up. So when we reflect the graph of cosine, it's going to actually be kind of the same idea, but the graph of cosine is going to end up looking something like this, where it's going to start way up here. It's going to start at pi, and then it's going to go down to 1. So it's going to start way up here, and it's going to go from -1 to +1. And it is going to stop here, because then it would curve back down and it would start repeating itself. So it is going to go from -1 to +1, and it's going to go from pi to 0. And then this part right here is pi over 2. So this is just what the graph of inverse cosine will look like. But notice now that this only exists in quadrant 1 and quadrant 2. So this exists solely in quadrant 1 and quadrant 2, which that makes sense because that's where the graph is. This is why I'm having a hard time with the sine being in quadrant 1 and quadrant 3. So I just want you to make sure that I will come back and talk about quadrant 1 and quadrant 3 versus quadrant 1 and quadrant 4 like your book says. But in this case, we can very, very easily see that cosine exists in quadrant 1 and quadrant 2. Okay, so cosine exists quadrant 1 and quadrant 2. All right, so that's just something to kind of think about, something to kind of deal with, something to kind of use, and hopefully it starts to make sense as we kind of work our way through. All right, so as we work our way through with these different ideas, these different thoughts, we need to be able to understand that there may only be, like we may be given a value or given an idea, and in that specific value or idea that we're given, we have to pay attention to where the quadrants may possibly exist. We have to pay attention to where certain values may exist with these types of ideas. Okay, so as we work our way through, we might be asked to find exact values of things. So we may be asked to find something like the inverse cosine of the square root of 2 over 2. So I might be asked to find that exact value, right? And if I'm asked to find the exact value of the cosine of negative, or the inverse cosine of square root of 2 over 2, you have to think of this being cosine of x is equal to the square root of 2 over 2. So you have to look at your unit circle, and in your unit circle, you have to pay attention to the fact that I am looking for an x value of the square root of 2 over 2. Now, obviously, this is positive, so it's telling me on my unit circle where this is going to exist, and this is going to exist somewhere in quadrant 1 with the square root of 2 over 2 as my value. So in my specific value, it's telling me that it's going to be pi over 4. So it tells me that it's going to be pi over 4, right? Because cosine of pi over 4 is equal to the square root of 2 over 2. So now I'm allowed to keep things exact very, very easily and without any real big issue, okay? So without any super big issue, I'm able to decide exactly what that angle is exactly in the form of a radian, all right? So that's just something to kind of think about. That's something that you should be able to do. That's something that you should be able to figure out. Your calculator or your book is also going to ask you specific things about finding values using your calculator. I'm not going to waste your time using your calculator or I guess teaching you, because you know how to find inverses with your calculator, right? That's what you did all of geometry. Just make sure you're being really, really careful with what quadrant you're dealing with. Make sure that you're being really careful, or I guess maybe not what quadrant. Be really careful with referencing, because sometimes reference angles can be kind of dicey and kind of an issue. So just kind of pay attention to that, because that could pop into a different, more tough idea. All right. The last thing that I want to do is I kind of want to introduce compositions. I'm going to go through one example of these. and then we'll pick that up on Monday. So I just kind of want to introduce this so you can see it. And then once you see this, hopefully it kind of makes sense as we work our way through. All right. But as we talk about these and as we look at these, I might ask you something like this: to find the tangent of the inverse cosine value of 2/3. So I might ask you something like this: to find the tangent of an inverse cosine value of something. Now, obviously, when you have parentheses, you should deal with the inside of the parentheses first. So dealing with the inside of the parentheses first, I'm basically saying right here that the cosine of x is going to equal 2/3, right? If the inverse cosine of 2/3 is equal to x, then the cosine of x is equal to 2/3. So what I would do with this is I can very clearly see that with inverse cosine, I'm dealing in quadrant 1 and quadrant 2. So since I'm dealing in quadrant 1 and quadrant 2, that specifically means that I am going to have a positive x value like this. I'm going to have a hypotenuse of 3, and then I'm going to have to find my sine value. I'm going to have to, guys, can you be quiet, please? So I know that I have my 2 here, and then I'm trying to find the x value, right? Because if I can do this, then I can very obviously find out what's going on. But I use the inside part of this to calculate this triangle and figure out this triangle. So now I know that x squared plus 2 squared is going to be equal to 3 squared. So I'm going to get x plus 4 is equal to 9. So then I know that I have x squared equals 5. So I know that that value is going to be the square root of 5. So that tells me everything that I need to know. And now if this was my angle that was in question, now basically I'm just saying tangent of this picture, right? Tangent of theta, because I want to figure out what's going on with this picture. So now if I look at my picture, I can find the tangent with opposite over adjacent, so I can do the square root of 5 over 2, right? So if I'm looking at the tangent of whatever this value is, I have found out pretty clearly that the tangent is equal to the opposite over the adjacent, and I've just used the cosine value to create my right triangle trig problem, okay? So that's basically what I'm looking at. That's basically what I want to figure out. That's what I want you guys to try to look at. I am going to check in as to why it is the first and fourth quadrant versus the first and third quadrant. The only thing I can think of right now is if I am dealing in the first and the third quadrant for sine, so this and this, if I'm dealing in the first and the third quadrant, so like if I have an angle like this, or if I have an angle like this, those values are going to technically end up being the same because this is going to be a negative x and a negative y, and this is going to be a positive x and a positive x and a positive y, which is going to actually create the same kind of ideas. And if I'm dealing in the fourth quadrant for sine, that is going to allow me the option of having a negative value. So that's what I'm thinking right now, but I'm not positive as to for sure example of that. So I'm going to come back to an example of that with you on Monday. All right. So anything that has to do with fourth quadrant inverse sine right now, just wait on it and we'll come back and we'll talk about that. I want to make sure that I have a good answer for you when we come back on Monday. Cosine should be all set. Any tangent values and things like that should be all set. Make sure that you're paying attention to that worksheet that I gave you on Google Classroom because that'll help you out with a lot of things. Okay. Does anyone have any questions about anything as we sit here right now?
In the problem we just did, like the composition, when we were given inverse cosine, why did we keep it the same? Like
why did we keep the same?
Like why is it still 2/3?
I don't know what you mean.
I don't know how to say it.
So remember, if I put inverse cosines like this, like if I do inverse cosine of 2/3, that is the way that we solve for an angle, right? If I have an inverse value, that inverse is how we actually solve for an angle. So basically here, this is just a really fancy way of them saying tangent of some angle, and I'm using the cosine value to come up with what that angle actually is. So this is the thing that gets plugged into right here. So cosine inverse, or the inverse cosine of 2/3, is an angle. It's that angle right there. And I'm using the tangent of that angle to figure out the exact value of what that value for tangent actually is. Does that answer your question at all?
Yeah, that makes sense.
Okay, cool. All right, so I'm going to stop recording here.